So let's sort of say where we're at right now. So we've been learning how to solve some of these differential equations, and we've been focusing so far on first order. Pretty soon we're going to expand our horizon a little bit and to second order. But at this stage we could say, there's two kinds of differential equations that we like. And when we say that we like them, we can actually solve. We like things we can answer. So what are they? Well, they're actually here. One of them is separable. We like separable differential equations because there's a technique to solve them. And the other one is the one we just finished, linear first order. So those are our two ones that we like. And when I say we can solve them, up to our ability to do integration. So in theory, yes, they can be solved. In practice, well, we have to have some reasonable type problems. So not every differential equation that we encounter that's first order falls into these categories. And so one of the things that we might want to do is say, well, can we sort of help gently massage them to get them into one of these categories? So that's what we want to talk about today. So there's this notion of substitution. And you might say, hey, I've heard of substitution before. Substitution is this really cool idea in calculus that helps us say, look, I can simplify the integrals. And so that I can transform something that looks really messy to something that looks slightly less messy. And it's the same philosophy in play here. It says, okay, look, let's look for a new variable to introduce and see if we can't make our differential equation somehow nicer, something that we can solve. Now, there's a couple of things that we should think about when we think about substitution. One thing, of course, is when I think about substitution, I always like to think of it's an inside job, right? So what does that mean? Oftentimes when you're looking for what kind of substitution to make, there's some notion of look for the inside function. And we'll see that showing up today. The other thing, of course, to remember with substitution is you have to substitute everything. And in other words, you can't just say, well, some of the places where that variable shows up I'll replace, and other places I won't. No, you gotta get everything updated to your new variable as is appropriate. Okay, so what we're going to see is going to be sort of a potpourri, a collection of things that we can do. By no means all, but these are some that are common. We probably won't do all of them today. I think we will spill over into next week. But looking at what we have on schedule for next week, that won't be an issue. Okay, so the first one says, well, suppose that we have a differential equation. And when we look at our differential equation, we see this sort of expression showing up, ax plus by plus c. And it's showing up sort of inside of functions. And we say, all right, well, that suggests that since that's showing up on the inside of functions, that we should do a substitution. And so in particular, when we were talking about what do we mean when we say it's showing up inside of functions, what that says is we have like our differential equation y prime is some expression where it's a function of ax plus by plus c. So what happens? Well, we say, okay, we make our substitution, and we say the inside thing is our substitution. And now comes the time when we have to think about, all right, what's going on here? Because we have some variables here. We want to keep track of saying what variable is our sort of input variable, what's our output variables. So when we think about a differential equation like y prime equals something, well, it really says, hey, we're really thinking about how y changes with x. So we just think of things as being functions of x. So when we're writing this z equals ax plus by plus c, there's this sort of inherent idea. This really is ax plus by of x plus c. And really our z is a function of x. So that we're really thinking, okay, it's x is still our sort of variable in play. So in particular, what's happening here is what I'm trying to get at is we introduce a new variable z. which variable is being replaced. And so the variable that's being replaced here is we're going to let y go to be in terms of z. That's the goal here. So we're replacing the y variables. All right, well, now you can see we have an example coming up in the very near future. And is it of the right form? Yeah, like we have this 4x plus y inside of a function square. And you'll notice this differential equation as written, is it separable? No. It's not separable. Is it linear? No. It's not. All right. But doesn't mean we can't do something. That's why we have this whole story going here. So the point here is all the y's become z's, which means we have to say everywhere there's a y, and there's two places, I have to account for that in terms of the new variable. So now we have to say, well, what's happening to the y prime? And so when we did substitution for integration, we said, oh yeah, remember how we have to have like dx become something du. It's the same idea in play here. All right, so we say, all right, take derivatives. So derivative of z, z prime. Derivative of ax is a, because we're taking our derivative with respect to x. Derivative of by is by prime, because again, we think of y as a function of x. And the derivative of c, well, that's a constant. And what do we end up with? Well, okay, z prime equals a plus by prime. So that lets us say, hey, I can solve for y prime. So I can replace y prime with this expression. Now, what's the great punchline here? It says, hey, check this out. Notice if I have this very generic statement here. What happens? Well, this would become 1 over b z prime minus a over b, that's that y prime, equals, on this side, what do we have? F of z. Now, what kind of differential equation is this? Can we say anything about this differential equation? I'll use my advanced marker technology to move the a over b across. Okay? Whoops. Okay. The technology fails. That's always happens. All right. So I can move the a over b across. What do we see here? What is this? It's separable. Because notice there's no x. So there's a dz dx, so I can move the dx across. I can move this whole expression over to the other side. We can separate this. This is separable. And why does that make us happy? Well, it makes us happy because we can solve separable. So that's why substitutions like this turn a problem from a hard one we can't do to one that we can. So let's carry this out. Let's see if we can do this. All right, so we see our substitution. No surprise, we look on the inside and say, hey, there's our substitution to make. So we'll make it z. Or if we're, feeling very British, we can say, okay, make it z. All right, just whatever you feel like that particular day. All right, so z, y plus 4x. All right, so that says z prime equals y prime plus 4, or y prime equals z prime minus 4. So we replace the y prime. That will be z prime minus 4 equals 4x plus y quantity squared becomes z squared. All right, well, maybe we can solve this. So this becomes z prime dz dx. Move the 4 across. Equals z squared plus 4. What happens next?
You can factor it.
We can? Well, I guess you can.
It's separable now between z's and x's.
Yeah, it's separable, so we separate. So we'll do dz over z squared plus 4, get all the z's together, equals dx. So that's our separate. What comes after separate? Integrate. So there's two sides. I'll do one side if you do the other. You'll do the right? What is that? X plus c. All right. Does anybody know kind of what this should feel like? Yeah, it should feel like arctangent. The 4 makes you have to fudge a little tiny bit, but just a little tiny bit. So this becomes, let's see, what is it? 1/2 arctangent of z over 2. So you have to account for that 4 on the inside. And that takes care of that. All right, well, okay, clean it up. Multiply both sides by 2. This becomes arctangent of z over 2 equals 2x plus c. Is that right? Yeah. And you might say, hey, shouldn't it be 2c? And that would also be right. Because c is a constant. And constants can absorb constants. Now, let's go a little bit further. We don't have space, but we'll pretend like we did. And, okay, how do I get rid of arctangent? Use tangent, so z over 2 is equal to tangent of 2x plus some constant c. Or z is equal to 2 tangent of 2x plus c. So is that our final answer? No. Why not? We did our substitution. So when we do substitution, we have to go back to where we started. Where did we start? Z equals y plus 4x. So we got to bring that back in. So y plus 4x equals this other stuff. And so we come to the conclusion that y is negative 4x plus 2 times tangent of 2x plus c. And there we go. There's our answer. Done. Success. All right. Good. Good. Well, that didn't seem so bad. We can do this kind of stuff.
Do we have to worry about, like, since arctan and tan, there's different, like, domain and range?
Well, in some sense, arctangent, we can have anything come in, so we're fine.
So is that only the other direction?
Yeah, you got to be a little bit careful, but don't stress too much about it. It works itself out. Initial conditions help you work it out. All right, so that's one example. So when we have something on the inside, that looks like, you might call this a linear thing. And of course, that was the easy stuff when we did integration, but of course, things can get more interesting. So our next example. So we say that a differential equation is homogeneous if it can be written in the form of y prime is some function of y over x. All right. Well, what do we do? Well, you might think, let's do the inside. And in other words, y over x is the inside function, so we'll call that inside function z. And yes, that's it. That's what you do. Great. Let's follow what happens. All right, so z equals y over x. Well, you can imagine multiplying. Y equals x times z. And again, we're thinking that y as being a function of x. So y of x equals x times z of x is how we should be thinking of this in the back of our heads. So, take the derivatives. Well, derivative of y is derivative of y. What rule do you need to take the derivative of x times z? Product rule. Derivative of the first is 1 times z plus the first times the derivative of the second. All right, so there we go. So that's going to be our substitution. Let's just see what our differential equation became. So we got to replace. There's a y in the y prime. There's this y showing up here in that f of y over x. So the left-hand side becomes z plus x z prime. So I'm just replacing the y prime by what it is. The right-hand side becomes f of z. Now, we won't go very far. Just want to go far enough to say, is this nice? So what can we do to say, yes, this is nice? Is it linear first order? Depends on what this is. If this is a constant, yeah, it's linear first order. If it's not, not so much. You got to be careful. But what can we do?
Separate.
How? Oh yeah, let's take the z to the other side. That's a good idea. So we'll leave the x there and we'll say that's dz dx. And that's f of z minus z. And now we say, oh look, the x dx can move across and the f of z minus z can move across. So this becomes dz over f of z minus z is equal to dx over x. And what do we see? We see it's separated. So yes, this is nice. It's separable. And so, aha, we're happy again because we're back to our, we can solve this. We can make progress. This is good news. Now we should pause and say, this word, homogeneous, it's kind of a weird word. Well, there's a couple parts. The first part, homo, what does homo mean?
Same.
Means the same. And then you have genius. Well, what does that mean? So let me explain what that means. So we can talk about this in terms of polynomials. So it's the same genius, which really you should think of as the same power, same degree. So I'll give an explicit example. We can make one up here. So suppose we have x to the 7th, all right, as y prime, plus 5 x squared, y to the 5th, equals 3x y to the 6th. Oh, sure, we'll throw in a y to the 7th here as well. Okay. Now, let's talk about the degree of these pieces. What's the degree of x to the 7th? 7. Now, the next thing, you have x squared y to the 5th. And you're like, well, wait, what do you do? Channel your inner, Captain Planet. And their powers combined, right? So, combine the powers, what do you see? 7. Here? 7. Here? 7. So this is homogeneous because they're all acting like something to the 7th. It's being split up in different ways, but it's all being the same behavior. And now, since they all have that, what you can do is, if that's the case, you can transform it to look like this. And the way you transform it is you just divide everything by the appropriate term. So in this case, I'll divide everything by x to the 7th. And you'll see, lo and behold, you'll get y prime plus 5. What happens here? What do you get? Y to the 5th over x to the 5th. Or y over x to the 5th. Equals 3. What happens here? Y over x to the 6th. And here? Y over x to the 7th. So in other words, it's exactly of this form. So that's what it means when it's talking about homogeneous. All right, good. Now it doesn't just have to be polynomials, but that's where the expression comes from. All right, so let's see if we can make a little bit of progress on this problem. Solve x minus y times y prime equals x plus y. Well, is it homogeneous? I mean, hopefully it is, because that's on this other side. All right, someone's saying yes. If you think about our pieces here, you have x, you have y, you have x, you have y. What are the degrees? They're all one. They're all the same. So since they all have the same degree, yeah, sure, it's homogeneous. So, all right, so what can we do? Well, we can do a couple of things. Depends on how you're feeling. So give me a suggestion. I'll follow your suggestion. You want to divide everything by x? Yeah, sure. We can do that. Divide everything by x. Now you might be saying, wait, you didn't divide this y prime by x. Well, it's equivalent. I'm taking 1 over x times both sides. If I took a divide by x by the y prime, I'd have really a 1 over x squared on the left and 1 over x on the right, and that wouldn't be the same thing. I would have done two different things to the two different sides. So 1 minus y over x times y prime is equal to 1 plus y over x. And we say, aha, great. Everything looks like y over x. So we're going to make our substitution. We follow that through. And let's see where it takes us. So our substitution says we're going to let z equal y over x. And we have that y prime is going to be z plus x z prime. So what do our pieces become? 1 minus y over x becomes 1 minus z. Y prime becomes z plus x z prime, the thing that I wrote, someone pointed out, equals 1 plus z. And notice we're now only in terms of x and z. So now we're great. We've changed it. There's no more y's left, so that's good. Whenever we do a substitution, we've got to get rid of one of the variables. In other words, we're substituting out. From here, let's do a little bit of distribution. So this can become z minus z squared, and then plus 1 minus z times x, z prime, equals 1 plus z. So far, so good? Are we all right? Z's cancel, and we can move the z squared across. So we get 1 minus z times x times z prime equals 1 plus z squared. Oh, this is feeling great. Or a little bit more, 1 minus z over 1 plus z squared dz is equal to 1 over x dx. So there was some dividing, moving things around, but that's what you'll end up with. Okay, are you satisfied? Could you finish it from here? Do you want me to keep going, or do you want to see more? We may not have time to go through all the examples all the way. All right, so I'll just say from here you integrate both sides and dot, dot, dot. And once you're at the end, what do you have to do? Make sure you substitute back after you do the integration. Now, the integrals themselves aren't terrible, but they're not trivial. 1 over x is straightforward. How would you integrate this left-hand side? Split it up. 1 over 1 plus z squared becomes arctangent. Good. Z over 1 plus z squared. Do you use substitution, and you'll be fine. It turns out to be 1/2 log of 1 plus z squared when you integrate. All right. So, another problem. Make substitutions of the form x equals u plus h and y equals v plus k, where u, v are variables and h, k are constants, to solve dy dx equals 2y minus x plus 7 over 4x minus 3y minus 18. Okay, so it's telling us these substitutions to make, and it's being very clear here. The u, v are variables, so essentially we're just changing x and y by shifts, is what we're doing. And h and k are constants. Now, which constants? And the answer is, we get to pick. You might say, well, let's just pick 0, Steve. Well, if you pick 0, do you gain anything? Yeah, it's just changing names, which usually does nothing for us. We want changing names plus. Something that gains us an advantage. All right, well, let's take a look at things we can say. If x is equal to u plus h, what can I say about dx? It's du. If y equals v plus k, what can we say about dy? dv. What can we say about dy dx? It becomes dv du. Because we're changing the order here. So it's like, great, I can change to dy dx. All right, that doesn't seem to really care what h and k are, because that doesn't care what h and k are. All right, well, let's look at the other piece. So, the right-hand side. So this is going to become 2 times u plus h. Oh, whoops. I can read. That's a y. So that's going to become v plus k. 2 times v plus k minus u plus h plus 7. Downstairs, 4 times x, that's going to become 4 times u plus h, minus 3 times v plus k, minus 18. All right, well, let's expand that a little bit. We get 2v minus u. I'm just looking at things that are variables. Plus, then at the end, we'd have 2k minus h plus 7. Those are the constants all grouped together. Downstairs, we'd have 4u minus 3v. And then we'd have the other stuff, 4h minus 3k minus 18. Okay. Well, what would we like to be true?
That 2k minus h is equal to negative 7 and 4h minus 3k is equal to negative 18. I mean, positive.
So there's a suggestion that says, hey, I'd like these things to be 0. In other words, I want it to look like that. Well, why does looking like that make us be like, yes? Well, what's good about this?
It just involves the variables.
Yeah, it's simpler. It just involves variables. In fact, it's even really good. Okay, well, we'll get to that. I'll let you think about it for a moment. Why is this one really good? It's like, oh, this is in our wheelhouse, so to speak. Okay, so now we have sort of an idea, a goal, a plan, which is, let's make these 0. And how do we make this 0? Well, what do we get to choose? So we get to choose h and k. And notice, there's a nice little thing happening here. How many things do we want to be 0? There's 2 things we want to be 0. Well, how many choices do we get to make? 2 choices. So there's 2 things we want to have happen, and there's 2 things that we can make happen. That's good. They line up. So there's a chance. There's a chance. All right, so the first equation would say, look, I want h minus 2k to equal 7. So that's equivalent to saying I want that to be 0. And the second equation would say, hey, I want 4h minus 3k to be 18. And again, that's equivalent to saying we get 0. Which one?
Should it be equal to minus 7?
Well, notice here, I moved the h and the 2k across. And then over here, I moved the 18 across. And you're probably thinking, why did you do that? Well, to get maximum confusion. I mean, no. I did it because I wanted just the leading coefficients to be both positive. That's why I did it. Okay, so 2 equations, 2 unknown. I should tell you right now, you're going to see this a lot, especially coming up in future topics. We're going to have lots of equations and lots of unknowns like this. So we want to be really, really comfortable at solving for things like h and k here. What can we do to solve for h and k?
Multiply the top one by 4 and subtract.
Okay. So in general, there's two strategies that you can think of. One strategy is substitution. And that strategy says what? Well, solve for h in one, plug into the other. That's the idea of substitution. And the other one, which is in my mind the better strategy, is linear combos to get 0. In other words, we're going to say, let's combine these in such a way that we knock something out. So someone said, hey, multiply this first one by a 4. Why? Because then we have 4 h's. They're both 4 h's. And now we're going to combine them in such a way that we're going to take the first one and subtract the second one. So what happens to the h's? Gone. Beautiful. All right, now let's see about the k's. What do we have? Minus 8k plus 3k. So be careful with the signs. Giving us a total of minus 5k. Equals 4 times 7? 28. Minus 18? Gives us 10. So what can we say about k? K is negative 2. All right, if we know k, can we find h? Yeah. Lots of ways to do it. One way we can do it is substitute in. So for example, we can say, look, I know k is negative 2. That says h, negative 2 times negative 2 is 4. So h plus 4 equals 7. What does that say about h? H equals 3. So we say, aha, we make a little note. Our real substitution was u plus 3 and v minus 2. So that's our real substitution that we make. And after we've done that, lo and behold, what we get is that dv du, that's what the dy dx becomes, is equal to 2v minus u over 4u minus 3v. We've simplified it out. We don't have those plus constants anymore. Well, how can we integrate this? What does this look like?
Separation.
It's not quite separation yet. Not separation yet. What could it be? What could it be? Sorry, what? Oh, it could be homogeneous. Yeah, maybe it is homogeneous. Okay, now how could we tell if it was homogeneous? What would we need to have? We'd want these things to look like v over u. We'd want everything to look like v over u. Can we transform this so everything looks like a v over u? How do we do it? Sorry, what? Multiply?
Oh, I was going to say multiply the 4u minus 2 on the other side and divide everything by u.
Oh, we can do that, yeah. I was thinking of, there's this old trick I learned in my younger days called multiply by 1. It's a cool trick. And you might say, that doesn't change anything. Aha, but a well-chosen one. What's a well-chosen one?
4u minus 3 over 4u.
That might not be. How about 1 over u? Multiply top and bottom by 1 over u. What does the top become? 2 v over u minus 1. And downstairs we have 4 minus 3 v over u. And now notice everything where our variable occurs, it is of the form v over u. So this is homogeneous. And we're off to the races because we know how to do homogeneous. We make the substitution and life is good. And I won't go any further at this point in time. But okay, good, good. Well, what a problem. That was fun. So, on to another kind of substitution. And this one is interesting. A little unexpected. So a Bernoulli equation is a differential equation which can be written in the form of y prime plus p of x y equals q of xy to some power. Now, you might think of this n as being like a whole number. No, any number, like a half, 2/3, 17, any power here. And we say, oh, wow, amazing, amazing. Our goal is we want to solve it. Okay. Now, we've solved some special cases. So, for example, n equals 0. Can we solve that? Yeah, that's our linear first order. We're like, yeah, we can solve that. Even if n equals 1, can we solve that? Yeah, we can, because we can move this p of xy across, and then it's become separable, because we can factor the y out. So we're like, well, we can do it for 0, we can do it for 1. Why not do it arbitrarily? Dangerous idea that just because it works for 0 and 1, it works for everything. But okay, so here's how it works. We're going to make a substitution. And this one, I would say, is kind of a non-obvious substitution. Now, there's two reasons I say that. That's the substitution we want to make. Z equals y to the power 1 minus n. That's not obvious. But there's another reason why it's going to be a non-obvious substitution. Do you notice something about this? It has a name. And whenever you see a name attached to something, that means this is not easy. They don't put names on things when it's easy. You know, it's not like, you know, Greg added 17 plus 12 and got 29, so they call it Greg's number. You know, no. You gotta have at least 4 digits before they start naming numbers after you. So it's a challenging thing. So don't think like, oh, this is totally obvious that this would work. Now, on a side note, I checked earlier today, and it turns out, so in academics, that you can trace what you call your academic ancestry, like who was the person who mentored you, who mentored them, so forth and so on. And so if you go back about a dozen generations in my academic ancestors, you get to Johann Bernoulli. Not this Bernoulli, but his brother. So his brother is one of my academic ancestors. So there's been knowledge passed from generation to generation. So you might say, okay, Steve, give us the secret knowledge. How did Bernoulli come up with this? And the answer is, he tried a lot of stuff, and this worked. So that's how math works. You try a lot of stuff, and you're like, hey, this thing works. And then you just tell people about your successes. Don't mention your failures. And people will think you're genius. All right. So let's just follow through. So again, we're thinking of these as functions of x's. So this is y of x to the power 1 minus n. And, well, what do we have? Take a derivative, z prime. That's not so surprising. On the other side, we have to do a chain rule. 1 minus n comes down. Subtract 1 from the exponent. That becomes y to the minus n times root of the inside y prime. All right. So that's the z prime. And now we say, okay, how does this transform? So let's go ahead, and I'm going to start by saying, take your original equation and multiply everything by 1 over y to the power n. And let's see what we have. So if we do that, we have 1 over y to the power n, y prime, plus p of x. And here I have y to the 1. Downstairs I have y to the n. I can write that as y to the power 1 minus n, just combining. On the other side, the y to the n's cancel. So we get q of x. All right, y to the power 1 minus n. What can we do with that? It's z. So we have a z. 1 over y to the n times y prime. Well, notice we can rewrite this as 1 minus n times 1 over y to the n times y prime. So what does this become? It's z prime plus, you got to correct for this constant. But that's a constant. We like correcting for constants because those are relatively easy. So it's 1 over 1 minus n, that constant, times z prime. And then so we have plus p of x times z equals q of x. Now, what can we say about this? Someone asked the question, is that linear? Is it?
Yes.
Yes. This is a first order linear equation. And what do we like about first order linear equations? We can solve it. So now we're like, aha, we can do it. We have the technology. Okay, so let's go ahead and run through an example. Try to do it relatively quick because we still have one more thing we want to do. Okay, so notice, is this a Bernoulli equation? Probably, yeah, I like that answer. We just talked about it, and now we're doing something. Odds are, probably has something to do with it. And it is, and in this case, n equals 4. All right. So, what's our substitution? Well, we're going to substitute z equals, according to this, y to what power? To the negative third. Right, because it's 1 minus 4. So y to the negative third power is our substitution. So we can do our z prime, negative 3, y to negative 4, y prime. That's what it'll turn out to be. All right, so we look at this, we say, okay, divide everything by that y to the 4 to help us get started. So we have x squared over y to the 4 plus 2x over y cubed equals 5. Oops, I forgot the y prime on the first term, but thankfully I had space in front. So, what does the first term become? If we're being careful here, we want to be careful. We want to make sure we get all our points. So there's the y prime, y to the 4th downstairs. So what's left? Negative 1/3. There's the x squared, z prime. Okay, the next term, 2x over y cubed becomes 2x times z. All right, y to negative 3, which is what you see here, is z. And the 5 becomes 5. That is correct. 5 still stays as 5. Good. All right, you cracked that code. And so now, from here, you'd say, okay, well, if we were going to keep doing it, we'd say multiply everything by 3, negative 3, divide everything by x squared. So you'd have z prime minus 6 over x, z is equal to minus 15 over x squared. Our integrating factor, well, would be e to the integral of negative 6 over x. Can you see what that integrating factor will become? Right, negative 6 ln x, which is the same as e to the natural log of x to negative 6. So 1 over x to the 6. So multiply everything by 1 over x to the 6, you get 1 over x to the 6, z prime minus 6 over x to the 7th, z is equal to negative 15 over x to the 8th. Wow. But the left-hand side is not so bad. That's 1 over x to the 6th times z, and take the derivative of that. That's, like I said, not so bad. That's going to equal to negative 15 over x to the 8th. What's the next thing for us to do if we're doing our technique? Integrate. So we put a lot of work to say, hey, that left-hand side looks an awful lot like a derivative. So now our work pays off because we say that left-hand side is super easy. 1 over x to the 6th times z. Integral of negative 15 over x to the 8th. I know some people are like, I can do the plus c, Steve. Yeah? Okay, good. It will, so this has x to the power negative 8. So when you integrate up, have x to the power negative 7. So 1 over x to the 7th. What's the coefficient? 15 sevenths. Yes. Well, not all coefficients are nice. All right, so we end up with z. Multiply everything by x to 6. We get 15 sevenths times 1 over x plus some constant c, x to the 6. But are we done? We got that. Are we done? Are we done? Oh, right. We got to get back, because we made a substitution. So, z is 1 over y cubed. So finally, to get y, we can say flip it and then do what? If we flip it and then cube root. So our final answer is z equals the cubed root. And then we flip it. 1 over this stuff. 15 sevenths times 1 over x plus some constant c, x to the 6. Boom! Just like what we would have thought, right? Yeah. Probably not. Oh yeah, this should be y. But yeah, boom! Just like what we thought. All right. One last note for today. So, in some cases, it's possible to take a second order differential equation and turn it into a first order differential equation. So what's a really simple example? Well, suppose you have f of x, y prime, y double prime. Now, when you see this, you should just think of, oh, there's some expression. There's an x involved, there's a y prime involved, there's a y double prime. What is not involved? Y. There's no y. And we say, hey, so here's an idea. So we're going to introduce something called z. We'll let that be y prime. All right. So z prime is y double prime. And then we say, well, wow, hey, that really says this thing which involves two derivatives now just involves one, right? Because it's z and z prime instead of y prime and y double prime. So that's pretty straightforward. So what happens? Well, here's a quick example. There's no y, so z would be y prime. Z prime would be y double prime. So what we would say is like, hey, this is really x squared z prime plus 3x z equals 2. Now, can we solve this? Yes. It's linear. Now, I'll skip the step of finding the integrating factor and just say multiply both sides by x. Why? Well, because I did it earlier today. But the way you check is you say, hey, is this left-hand side a derivative? I claim it is. Is it a derivative of something? Can you see what it would be? X cubed z. First times root of the second, root of the first times the second. All right. Integrate both sides. What do we get on the left? X cubed z. What do we get on the right? X squared and c. Okay, so we get z is 1 over x plus c over x cubed. Are we done? No! Because we got to go back to our substitution. This is not z, this is really y prime. So now what do we have to do? How? Integrate. So what is y? Well, what's the integral of 1 over x? natural log of x. Integral c over x cubed. There's a minus involved. So it's x to minus 3. Add 1 to minus 3 would give us minus 2. So that's why it becomes x squared. Then you have to have the 2 there to count. Anything else? Another constant. And it's a new constant. We should expect 2 constants. Why should we expect 2 constants? Because it's second order. Whatever the order is, that's how many constants you should have at the end. All right.